we've been building a software rasterizer in Cuda for large amounts of triangles. And so there's a couple of reasons of why you might want to do that. And I'll just start with the real motivation that was not in the paper, because I thought reviewers might not appreciate it. And the real motivation is I'm simply not smart enough for Vulkan. So I was trying to find an easier way to render large amounts of triangles, and let's just compare how you do things in Vulkan and Cuda. So this is how you allocate memory in Vulkan, and to do the same thing in Cuda. So by the time you wrote a memory allocator in Vulkan, you could already write a software rasterizer in Cuda. So there's some interesting prior work here that we're building on, and one is FreePipe, which came up with the idea to use atomic min in order to store the closest fragment in each pixel. So here, for example, we have the depth value, and we convert it to an integer, and then simply use an atomic min into the pixel, and that way we get a depth buffer. The problem they had at the time was that there were only 32-bit atomics back then, but nowadays we have 64-bit atomics, which also allow us to store some additional payload, like the color value or the triangle ID. So nowadays, this is kind of the basis for many GPU-based software rasterizers. Two prominent examples here are Green's game for the PlayStation, and of course Nanite. So Nanite, I suppose everyone here knows it. It's a hierarchical level of detail system, and they software rasterize at least small triangles. And only when the triangles get larger, they fall back to hardware. And that's because they found out that if you have small triangles, you can be up to 3 times faster if you just render them directly in a compute shader. They also use a visibility buffer because it lends itself very well to this atomic min approach. So we are basically doing a lot of the same things, just without the level of detail part, because we're trying to just brute force render a whole lot of triangles without having to spend time to generate LOD structures. So let's try to render millions to billions of triangles brute force. For the kind of data sets we've been dealing with, so very large photogrammetry data sets, you have many triangles, a few pixels on screen, so you will end up with very small triangles. So the main goal is to make the rasterization of small triangles fast, but then still have fallback stages for larger ones, for example, if you zoom in. And we're also using a visibility buffer, where instead of storing any other attributes, we only store the triangle ID into the frame buffer, and with the triangle ID, we then can look up all the other attributes afterwards for the shading pass in a separate screen space pass. Okay, the whole thing was implemented in a 3-stage pipeline using 3 CUDA kernels. And in the first stage, we launched 1 thread per triangle. And this kind of assumes that the triangles are small enough that 1 thread can easily render them in very quickly. And this is not always the case. If triangles are larger than, for example, 120 pixels, we then instead put them in the queue for the next stage, where we then launch 1 warp for each of these triangles to have more compute powers for rasterizing them. But there might still be even larger triangles, so above, for example, 4,000 pixels. And in that case, we need even more compute power, and we get this by splitting up the triangles into smaller pieces and then launch 1 thread block for each of these pieces for rasterization. So the actual implementation for each of these stages is not too complex. So if you have done a software rasterizer before, there are not many surprises here. Except maybe that it's very simple. So we don't use some complex edge functions. We just iterate through all of the pixels in the bounding box of the triangle and stuff like that. So it's really a very simple rasterizer. So I will just focus on some of the maybe slightly unusual parts. For example, the visibility buffer precision. We have the 64-bit integers that we can store in the frame buffer with atomic min. So we have some bits we need for the depth value and some bits for the payload. And for visibility buffers, that payload is usually some bits for the mesh index and a triangle index within the mesh. Now the problem is we have some very large data sets, like the Sora data set with 18.9 billion triangles, which are split up into 26,000 nodes with up to 30 million triangles per node. So we would need 15 plus 25 bits to index all of these triangles. And that's already quite a lot. That only leaves 24 bits for a depth buffer. Can be fine, but the problem is that there might be scenes with even more nodes, so we need more bits for that. And there might be scenes with a higher maximum amount of triangles per node, so we might also need more bits for that. So what we decided to do instead is we store the global triangle index of each triangle into the fragments in pixel. And with that, we can use 36-bit to address up to 60 billion triangles. And these triangles can be distributed anyway in the scene. In theory, you could have 60 billion triangles distributed in 60 billion meshes. Although, of course, that's not recommended. After rasterization, we then have the resolve pass that converts this visibility buffer into a shaded image. And for this, we launch a CUDA kernel with 1 thread per pixel. And now we have the challenge that we store the global triangle index in each pixel. But we also need to find the mesh index. And we do this by doing a binary search through the prefix sum of all the triangles, of all the meshes. And basically, we take this global triangle index, check in the middle of this prefix sum. Is this the mesh index? Is this the mesh that has this triangle? If not, we continue the search in the left or right part. And this sounds a little bit expensive, but it's really not. So it wasn't a bottleneck in our testing, so we didn't bother trying to optimize this. And then, just some standard visibility buffer stuff. We load the triangle geometry, we project it to world space, and then we cast array through the pixel to the triangle to get the intersection point. And with that, we have all the information we need to do the shading. And since it's a visibility buffer, with the triangle ID, we can look up all the attributes that we might need for different kind of materials. So at that point, the major bottleneck might usually be memory bandwidth. So if you have small triangles, we don't need much compute power to actually render them. But we might still have to do a whole lot of vertex and index data loading. And one way to improve this would be compression, but another way is instancing. So if you have a scene with instancing, what you can do is let this rasterization kernel just load the triangles once into registers and L1 memory, and then rasterize just all of the instances. Just loop through the thousands of instances and then rasterize them. And with that, we have, for example, here a scene with one mesh with 1 billion triangles and 3,000 instances of that. So there's a total of 3 billion triangles that we brute force rasterize in just about 10 milliseconds. Another thing that we tried just recently, about 2 weeks ago, so it's not in the paper, is to do alpha blending, because every good real-time rasterizer also needs alpha blending. And for this year, we just simply implemented pretty much the same approach as Gaussian splatting. We split translucent triangles into pieces of 16 times 16 pixels, sort them by tile and depth, and then blend them together front to back. One of the issues here is that with the original Gaussian splatting, the splats were screen-facing, but with triangles, they might overlap. And to resolve these overlaps, to get the right order of the blending, we also need to do some pixel-wise sorting in addition to this tile-wise sorting. And we just took some inspiration here from some Gaussian splatting papers like Stop the Pop and Perspective Correct Gaussians. Basically, we just take a look at some of the next few triangles and only sort them, take the closest of these fragments, and as long as there aren't too many overlaps, you will get accurate blending. Okay, then let's have a look at some of the results here, some performance results. This is a walk through the Sora scene from NVIDIA. It has 18.9 billion triangles. And even this little object here in the scene already has a whole lot of triangles. So it might be, I don't know, it could already be a million triangles. There are multiple instances of that. And in general, many things in the scene have all of these ornaments with lots of triangles. So one thing we wanted to be able to do is we somehow obtain these data sets and we want to quickly take a look at them without having to generate LOD structures, without having to spend memory and time to generate them, just brute force them. So we can load this data set, 38 gigabytes from SSD to a GPU in 6.6 seconds and get our first frame, so basically in the 6.6 seconds. In this viewport here, there are 13.6 billion triangle visible. And these are rendered in about 55 milliseconds. So about 11 times faster than Vulkan in this case here. So then there's another interesting scene here. This is a photogrammetry scan of Venice. It has about 400 million triangles. So this is also a very dense data set. So here you can soon see the wireframe. So yeah, lots of triangles. And you could, of course, create a level of detail structure, but in the earlier stages, you still have to do some cleanup. You have to edit the mesh, and we want to be able to watch it in real time with brute force rendering. So with Cuda, we're able to render this in about 8 milliseconds, the original mesh. And with Vulkan in EGSR, it takes about 40 milliseconds. And here's also something that's a little bit unintuitive. So with Vulkan vertex plus index pulling, it's about double as fast as Vulkan index draws on the RTX 5090. So RTX 5090 got really good at index pulling. But after mesh optimization, index draw got faster than index pulling, but also Cuda still a little bit faster, about 3 times faster than index draws in Vulkan. Of course, not everything's better than hardware. So here we have a low poly mesh, a sponsor, and in this case here we're about 10 to 11 times slower than Vulkan. But I would say that nowadays meshes and scenes get more and more dense. So this is more like an outlier rather than the norm, I would guess, in the future. Okay. Then maybe one more interesting result here is that supersampling actually performs really well for these scenes here for brute force rendering. And in Sponsor, not so much, but in Venice and Sora it does. So if we take 16 samples per pixel, we're only about 15 to 60% slower. And that is because we have pixel-sized triangles, so we don't need much compute power to render them. And if we increase the samples per pixel, we're effectively increasing the triangle size, have more fragments, and we gradually shift the memory bandwidth to compute bottleneck. So yeah, then there's the question, of course, why actually can software rasterization be faster than hardware? And the thing is, I would like to know the answer to that too. I don't really know. There are many speculations for that out there that sound plausible. One of them is, for example, that it might be because of helper lanes. So if you have pixel-sized triangles and you still have the helper lanes for the traditional rasterization, you just have wasted effort. It might be a bottleneck, but I don't think it's the main bottleneck, because if you switch from vertex shaders to mesh shaders, you can still get twice as fast as the vertex shader approach. And also, as you've seen before, even index pulling can be faster than index draws for these very large data sets. And index pulling also doesn't use this input assembly here. So maybe the input assembly is the bottleneck, or maybe there's some kind of hierarchical rasterization process going on that's meant for larger triangles in the GPU pipeline. But if we have mostly small triangles, then we have some additional overhead that's not useful for our scenes anymore. So yeah, if you know the true answer of that, then please let me know. Yeah, and then thank you for your attention.
Questions?
Great talk, thank you. So, do you have any thoughts on what other parts of the conventional vertex pipeline, like tessellation or early Z or these sort of things, you might be able to implement faster?
Pardon me, what? Things like what?
Like tessellation or early Z culling or yeah.
That's a good question. So I mean, as long as it's workload that a single triangle can handle reasonably fast, I think it can be faster than a hardwired tessellator. So we've rendered triangles up to 128 pixels with a single thread. And I guess if you're tessellating things in that range, it could also be faster than a hardware rasterizer, but I don't know, so it's just a guess. Or maybe just to add to that, I think there are definitely things that won't be able to faster in software. Like the large triangles, I think the GPUs are too well optimized for that, so you'll probably never be able to do this faster in software rasterizer. And translucent ones.
Other questions? So what is the bottleneck in CuRast?
So it's still memory the bottleneck right now, mostly. And but there are already solutions out there that could address this. Like there is Mesh Optimizer, which can also generate meshlets and hierarchical clusters like Nanite. And I think this could also help CuRast become faster.
Any other questions? All right. If not, let's thank our speaker again.